Please press pause on the video. Okay, here we have a container, and we have a syringe again with a plunger on the top and some weight. And we have our nice little graph. So what I'm going to do is I'm going to adjust the temperature. The molecules are moving around, bouncing around in there, and they're pushing on all sides of the container, including the roof. And they're pushing so hard that they can lift up the weight. Well, what happens if I decrease the temperature? So we'll decrease it down a little bit. We're going to do this in 3 or 4 increments. So it's cooling, it's cooling, it's cooling. And there's our graph. It sort of looks like it might be linear, but we've had graphs that look like they were linear before. So let's get some more points. And our plunger begins to sink. The molecules are not moving as fast, and so they're not able to push up as hard. That means it takes more molecules, more concentration of molecules to be pushing in order to hold it up. And as we cool it some more, we'll have quite a drastic change here now. The molecules are moving slower, and so they require more of them to push against it. It compresses them. Okay, so here we have our graph. We'll close that. I'm going to show our data table, and we'll do the whole plot all together. When we have all of our points together, we can see a nice linear curve, a straight line, y is equal to mx plus b for our relationship between our volume and our temperature. So now we have our graph. When we turn to the question we had asked before, we had a prediction, which graph most represents the relationship between volume and temperature. It turns out that in our question, C most accurately represents volume and temperature. Okay, so let's look at a microscopic view. Here we have our simulation again from our microscopic view. We've highlighted one particular molecule so you can see how it changes as it collides. We have quite a large volume, and we're at a high temperature. Our graph over here has volume on the y-axis and temperature on the x-axis. Now, if we change our temperature and we cool it down, the molecules aren't moving as fast. The molecules aren't moving as fast, and so because they're not moving as fast, it requires more of them colliding in order to hold that thing up. Now, we clearly have not enough molecules. Right now, there's a moment in time where the top is not being held up by any collisions. It's because we're only showing some of the molecules. In reality, there's multiple moles of this, and so there's multiple decimal points here, multiple orders of magnitude of gases here. At any one particular point in time, there's a whole bunch hitting the wall, but in our little simulation, there's not enough to hold it. As we decrease our temperature, their velocities change, and it decreases. And so now, in order to hold up that top container, more molecules have to collide with the roof to keep it up. Now, don't confuse velocity of a molecule with the concentration. They're more tightly packed, and it's easier to get from side to side because it's a smaller container. That gives us the illusion that perhaps the velocity is either unchanging or maybe even increasing. That's not true. Okay? Just because they can get from one side of the container to the other doesn't mean that they're speeding up. It just means the container's getting smaller. So there's a little optical illusion there that some of us get tricked on. And if we cool it down even more, we get something like that. If we cool it down even more, Now they're moving hardly at all, and it takes a whole variety of molecules hitting the top in order to keep it up a little bit. Okay, so from what our simulation showed us, question number 4, what happens to the velocity of the particles as the temperature drops? You should press start on the CENTIOS. A, the collisions increase. B, the molecules slow down. C, the collisions decrease. D, the molecules speed up. Or E, there's no change at all. Please press pause. And so the answer is, as the temperature drops, what happens to the velocity? They slow down. Charles' law derivation. When we did Boyles' law, we looked at a pressure volume graph, and we took 2 points on the line, and we found something that was unchanging and made an equation out of it. Well, we'd like to do the same thing here. Here's our nice volume temperature graph, and we can use a straight line to connect those dots and see that we would have a nice linear relationship. So if we think about this for a second, slope would be rise over run, and so that would be volume over temperature. And since it's a straight line, it doesn't matter what 2 points I use, the slope is always going to be the same. So the slope for point 1 is going to be equal to the slope for point 2. What that means is we would now have slope is the same as volume versus temperature, and put some 1s and some 2s in there. And there we have our formula. V1 over T1 is equal to V2 over T2. And so this is Charles' law. Okay, so I have a question for you that I would like you to try and answer, a prediction. My question to you is, does the graph cross the x-axis? If it does, what would that imply? If it doesn't, what does that imply? Please click Start on CENTIOS. Here are your options. A, it will not cross the x-axis. B, it will cross the x-axis. C, the molecules occupy no volume. D, it's asymptotic. Asymptotic means it will approach but never cross. E, all molecules disappear. F, molecules stop moving. G, molecules occupy no extra volume. H, all of the above. There could be more than one right answer. You should select all of the correct ones. Press pause on the video. Okay. Now I've kind of asked you a trick question here because it's a little misleading. The question is, will it cross the x-axis? And what does that mean? Well, suppose we draw our graph and connect our lines, and we have it touch the x-axis. What does that mean? Well, if we start on the right-hand side, we have a certain volume and a certain temperature. If this is a balloon and we decrease our temperature, the molecules are not moving as fast, they're not pushing as hard on the outside of the container, and so the container shrinks. The container shrinks, it continues shrinking, and even when we get past into the 0, it continues to shrink, continues to shrink. If it gets to the x-axis, as is drawn here, on an elementary level, what that means is there's no volume. There's no volume. How can it not have any volume? You started with some stuff has some volume, and although in a balloon most of the space is empty, their molecules themselves do take up some volume, and so as I decrease them and squish them all together, they don't disappear. So from an elementary point of view, we would say that no, it can't cross the x-axis because that would mean that the molecules disappear. They don't disappear. They are there.